Last lesson, we talked about solving exponential functions. Today, we're going to talk individually about solving logarithmic functions. And we follow the same idea that we did with exponential functions. We're still going to isolate the logarithmic function if possible. And then if it's convenient, when we have both sides written as the log with the same base, then those equate to the same argument. However, if we cannot express both sides with logarithms, we will write them as exponential equations and then solve as we know how. So this first example, it says to solve the following, and then just like when we are solving exponential functions, we are able to check graphically, which has been super helpful for us. Solve the following equation and then solve graphically to verify. Here we have log base 117 of 1 minus 3x equal to log base 117 of x squared minus 3. We are written in logarithms, and I notice that our base is the same. So using the one-to-one property from lesson 6.2, this is the same as setting each of these pieces equal to each other. So 1 minus 3x is equal to x squared minus 3. Well, now it's in a quadratic. I'm going to leave my x squared positive and subtract 1, but add 3x to both sides. At the same time, I'm going to rewrite it in descending order so that I have x squared plus 3x minus 4, so that it's truly written in quadratic form. Perhaps I'll be able to factor. So find two numbers that multiply to -4 but add to +3. Here we would have 4 times -1, since 4 times -1 is -4, but when I add, I still have +3. In factored form, we'll have x plus 4 and x minus 1. Now that it's factored, we know we can set each factored piece equal to 0 and solve. So our choices are x is -4 and x is +1. We know we have to check our results. So I'm going to use -4 as my first piece to see if that is a valuable resource, and then I'll check 1 as well to see if that's valuable. When I check log of 117, I'll have 1 minus 3 times -4 equal to log of base 117 of -4 squared minus 3. Here we'll have log of base 117 of 1 plus 12 or 13. And log base 117 of 4 squared, or -4 times -4, which is 16. 16 minus 3 is 13, so this checks out. However, when I substitute 1 in, we're going to end up with a problem. We're going to have 1 minus 3 times 1. And when I simplify this, we'll have 1 minus 3, or log base 117 of -2. -2 is not in our domain. Our domain of logarithms is from 0 to infinity, and -2 is not in the domain. So 1 can't possibly work because it's not in our domain. That is why when I'm graphing, the answer of -4 is the only one we see, because when we substitute 1 in, it's not in our domain. I am also using the intersect method, where I set the left-hand side equal to one graph and the right-hand side equal to the other part of the graph, and find out where they intersect one another. And I do see they intersect at -4, which is what we found algebraically. Let's head over to slide 2. Here we have 2 minus the natural log of x minus 3 equal to 1. We need to isolate the logarithm. So to do that, I'm going to subtract 2 from both sides. I'll now have the natural log of x minus 3 equals -1. We'll want to divide both sides by negative to undo the negative in front of the natural log. I know that the natural log is the same as log base e of x minus 3 equals 1. This now allows me to rewrite this as an exponential. Notice that I don't have the natural log on the right-hand side, so we're not able to set those inner pieces together. But I can say that e to the first power is equal to x minus 3. And now we can easily solve for x by adding 3 to both sides. So x is approximately e to the first power, which is just e, plus 3, which is about 5.718. Utilizing the intersect method, notice I have the left-hand side of my graph and the right-hand side, and identifying where they intersect one another. The exact form is e plus 3, and the approximation is 5.718. So be careful how MyOpen Math is wanting you to write the results. Let's do another one where our logs are listed. Here I have log base 6 of x plus 4 plus log base 6 of 3 minus x equal to 1. What we can do at this point is use the product rule to combine our two logarithms together. By doing so, I will have log base 6 of x plus 4 times 3 minus x equal to 1. Since I don't have a logarithm on the right-hand side, we can write this as an exponent. So our base is 6 to the first power is equal to x plus 4 times 3 minus x. We can go ahead and distribute. 6 is then equal to 3x minus x squared plus 12 minus 4x. Rewriting and combining, I have 6 is equal to negative x squared minus x, I was on the right track, minus x plus 12. I typically like to have a positive x squared, so I'll add x squared and x and subtract 12 and bring them to the left-hand side to set it equal to 0. I'll now have positive x squared plus a positive x minus 6 equals to 0. We could now factor, so what multiplies to negative 6 but adds to positive 1? Let's see here, 3 times negative 2. Since 3 times negative 2 is negative 6 and 3 minus 2 is positive 1. So x plus 3, x minus 2 is 0. Setting both pieces equal to 0 and solving. X is then equal to negative 3 and positive 2. Regardless if I put negative 3 and positive 2 back into our x's, we'll still end up with positive values. So both of them are in the domain. I can also see that both of them are solutions with my graph as well. When I set the logarithms on the left equal to 1 on the right and identify where they intersect one another. Let's move to slide 4 where we can check out another example. This time I've got logarithms on both sides. However, one does not have a logarithm. So let's bring all of our logarithms together by adding log base 7 of 3 minus x to the left-hand side so that we have log base 7 of 1 minus 2x plus log base 7 of 3 minus x equal to 1. Just like the last example, we can use the product rule to combine these into one logarithm of log base 7 of 1 minus 2x times 3 minus x equal to 1. Converting into an exponential, I have the base of 7 to the power of 1 equal to 1 minus 2x times 3 minus x. Let's distribute to eliminate our parentheses. 7 is equal to 3 minus x minus 6x plus 2x squared. Combining like terms, 7 is equal to 2x squared minus 7x plus 3. We know we're going to have to factor and set equal to 0, so we'll subtract 7 from both sides. Therefore, 0 is equal to 2x squared minus 7x minus 4. We can try to factor. This time, since I have a value in front of x squared, we have to use the AC split method, where we find two numbers that multiply to -8, since 2 times -4 is -8, and yet adds to -7. Let's see, -8 times 1 would work. Since -8 times 1 is -7, we can split then our middle term. So 2x squared minus 8x plus 1x minus 4. Now that I have 4 terms, we can factor by grouping. The first two are divisible by 2x, and the second is divisible by 1. When I divide the first two by 2x, we're left with x minus 4. When I divide the second two by +1, we still have x minus 4, which is what we need to have a common binomial. Factoring out the common binomial of x minus 4, we have 2x plus 1 left. Setting them both equal to 0, our choices are x is equal to 4 and x is equal to -1/2. If I were to substitute 4, I would have 1 minus 2 times 4, or 1 minus 8. That would give me a negative in my logarithm, and that is not in the domain. That is not in the domain of 0 to infinity, so 4 is not a viable solution. Let's try -1/2. If I substitute 1 minus 2 times -1/2, we're going to get more positive since the double negative turns to a positive. Similarly, if I do 3 minus -1/2, again, we're going to get more positive with that double negative. So yes, -1/2 is in the domain, so it is a good solution. And we can even see it when we're using the intersect method. Notice I have log base 7 of 1 minus 2x on the left and 1 minus log base 7 of 3 minus x on the right, and then find where they intersect one another. All right. Here with letter E, we're going to tackle it the same way we have done C and D here, except this time we're going to be dividing, because if I want to get all of my logarithms together, I will have to subtract log base 2 of 6 minus x to the left-hand side. That will then give us log base 2 of x plus 3 minus log base 2 of 6 minus x equal to positive 3. We are subtracting, which tells us we need the quotient rule. The quotient rule tells us that we need to divide. So x plus 3 over 6 minus x equal to 3. We now can write this as an exponential. Our base is 2, so 2 to the third power is equal to x plus 3 over 6 minus x. I know that 2 cubed is 8, so 8 is equal to x plus 3 over 6 minus x. To eliminate our denominator, I'm going to multiply both sides by 6 minus x. I can distribute the 8 so that we have 48 minus 8x is equal to x plus 3. Add 8x to both sides. 48 is equal to 9x plus 3. Subtract 3, so 45 is equal to 9x. And x is equal to 5. Regardless if I put 5 into our parentheses, we'll still have a positive value, so it is in the domain, so it is a good solution. On the left, I graphed log base 2 of x plus 3, and then graphed log base 2 of 6 minus x plus 3, and found where they intersected one another. All right, I don't think you can ever have too many different types of examples, so apologize if you feel that this is too many. Here we have log base 125 of 3x minus 2 over 2x plus 3. What's wonderful here is that it's already like combined and used the quotient rule for us. At this point, we can turn it into an exponential by saying 125 to the power of 1/3 is equal to 3x minus 2 over 2x plus 3. I can turn 125 to the 1/3 power into 1 is on the inside and 3 is on the outside, or the index. This is the same then as the cube root of 125 to the first power. Well, the cube root of 125 is 5. So this is saying 5 is equal to 3x minus 2 over 2x plus 3. And then we can solve it just as we did the last example, where we multiply both sides by the denominator to eliminate it. Distribute our 5. 10x plus 15 is equal to 3x minus 2. Combine our x's together and our whole numbers. If I subtract 3x and then subtract 15, I will have 7x is equal to negative 17. So x is negative 17/7 in its exact form, or approximately negative 2.429, which is what we see when we intersect them. So again, be careful. Does my open math want the exact answer, or are they okay with the estimation? Our next example, you'll notice on slide 7, I have 1 plus 2 times log base 4 of x plus 1 equal to 2 times log base 2 of x. We have a problem, a big one. Our bases are not the same. And we know that they need to be the same in order to do anything with them. The first thing I'm going to do is subtract 2 log base 4 so I get all of my logarithms on one side. I'll now have 1 is equal to 2 log base 2 of x minus 2 times log base 4 of x plus 1. I'm going to use our change of base formula to make it log base 2 instead of log base 4. To do that, I will have log base 4 of x plus 1 is equal to log base 2, the base we want to have, over x times x plus 1, over log base 2, the base we want to have, of our current base. Notice that this bottom part might turn into a whole number since I ask 2 times what power gives me 4. And I know that 2 squared is 4. So this is really log base 2 of x plus 1 over 2. All right, let's bring it back. I have 1 is equal to 2 times log base 2 of x minus 2 times log base 2 of x plus 1 over 2. Which happy day allows us to eliminate the common factor of 2. I'm also knowing that, we'll just rewrite it here now that the 2 is done. Then we'll go to the next step. We have the 2 in front. Before we can create it and make one logarithm using the quotient rule, let's move our 2 back into the exponent so that we have 1 is equal to log base 2 of x squared minus log base 2 of x plus 1. Using the quotient rule then, we will have log base 2 of x squared over x plus 1. I now can write it in exponential form. Our base is 2, so 2 to the first power is equal to x squared over x plus 1. I can multiply both sides by x plus 1. I'm going to erase some stuff so I have more space. I now have 2x plus 2 equal to x squared. Or 0 is equal to x squared subtract 2x subtract 2. I cannot factor And notice that our answer is an ugly decimal, so I'm probably going to have to use the quadratic formula, where a is 1, b is negative 2, and c is negative 2. So x equals the opposite of negative 2 plus or minus the square root of b squared minus 4 times a times c all over 2a, or positive 2 plus or minus the square root of 4 plus 8 over 2, 2 plus or minus the square root of 12 over 2. 12 is the same as 4 times 3, and I can take the square root of 4. So 2 plus or minus 2 square root 3 over 2. I can factor out a 2 from my numerator, which would help eliminate the 2 in our denominator. So we have two results. Obviously, one of them is not going to work. I have 1 plus the square root of 3 and 1 minus the square root of 3. The square root of 3 is bigger than 1, so if I take 1 minus the square root of 3, I'm going to have a negative value. And if I stick a negative value in the second right-hand side, that's not going to be in our domain. So 1 minus the square root of 3 is not in our domain, so the only valuable resource or only valuable solution is 1 plus the square root of 3, which is in the exact form, and the about answer, or our rounded solution, is the 2.732. So that had a lot excuse me, that had a lot going on in there. All right, example 8. Here I have an inequality. Notice that when I solved this, I set it equal to or less than or equal to 0 here. So I brought everything to one side. So we're looking for where is our graph negative or below 0, and we can see where that's happening in the picture. Let's algebraically look at this. So I'm still going to do the same idea. I'm going to say 1 over the natural log of x plus 1 minus 1 is less than or equal to 0. In order to combine these two together, we need a common denominator. And our common denominator is the natural log of x plus 1. So this would then be the same as 1 over the natural log of x plus 1 minus the exact same thing over itself, because we know anything divided by itself is 1. This is then equal to, well, I'll have 1 minus 1, so those will end up disappearing. And I have 0 natural logs on the left minus the natural log of x on the right. So I have negative natural log of x over the natural log of x plus 1 on the right. And we're asking, where is this less than or equal to 0? We have a denominator that we're interested in. We want to make sure that this value is not equal to 0. So we want to avoid where it's equal to 0. We want to avoid where is the natural log of x plus 1 equal to 0 because we want to avoid that. I can subtract 1 from both sides. I know that the natural log is the same as log base e of x, so rewriting it as an exponent, I have e to the negative 1 equal to x, or x is equal to 1 over e. We want to make sure that we are not there. So I'm going to start drawing a number line so we can identify. We'll start with 1 over e. We do not want to have 1 over e. We also want to know where is our entire equation? Where is the negative natural log of x over the natural log of x plus 1? Where is this equal to 0? Because that's going to be another critical value that we're looking at, just as we did with rational functions. I can multiply both sides by the natural log of x plus 1 so that I eliminate it. And when I multiply 0 times the natural log, it'll still be 0. I can divide by negative 1. So I have the natural log of x is still equal to 0. Again, the natural log is the same as log base e. So e to the 0 power, where is that equal to x? Well, anything to the 0 power is 1. So we're also looking at 1. And it can be equal to 0. And it is less than or equal to, so that's okay. If it was just less than, we would have a open circle. We also know that our domain of natural logs are from where x is greater than 0. So we also want to include 0 because that's the domain of the natural log. And it's not, there's an asymptote there, so we know it's open circle. We know for a fact we're going this direction. But what's going to happen in between? 1 divided by e is approximately 0.368. So if I chose a test point of 0.25 and I chose a test point of 1/2, this will help us determine where we're negative and where we are positive. So if I chose 0.25 and I substituted that back into my function, we end up with a negative value. If I substitute positive half, we end up with a positive value. And, oh, we need to know what happens over here too. So let's do 2. We end up with a negative value. We're looking, where is our graph negative? It's a negative in these two intervals. So it's negative from 0 to 1 over e, union 1 included, because it's okay for the whole thing to equal 0. We can also see that 1 is on the graph itself, to positive infinity. So 1 over e is acting as a vertical asymptote that we wouldn't know specifically what that number is unless we algebraically solved for it, just as we did in these steps here. So we can see that our graph is negative from 0 in this little area here. And then it picks up back negative again from 1 included through infinity in this little area. Here we have log base 2 of x squared is less than 2 times log of 2 of x plus 3. Let's go ahead and bring everything to one side, just as I did in here, and we're going to say, where is this less than or equal to 0? We can even see that it is less than or equal to 0 in between half and 8. So that's kind of going to be our goal. When I subtract, I'll have log base 2 of x squared minus 2 times log base 2 of x minus 3 is less than 0. Notice that log base 2 of x is kind of acting in a way like a quadratic. So let's let u equal log base 2 of x. And if we square both sides, notice we get exactly what we have. So I could say that this is u squared minus 2 times u minus 3. Or I could easily factor what multiplies to negative 3 and adds to negative 2. Negative 3 times 1. So u minus 3 times u plus 1. When I solve them, I'll have u is equal to positive 3 and u is equal to negative 1. Well, our u value is really log base 2 of x. So log base 2 of x is 3, and log base 2 of x is negative 1. Rewriting this then using exponents, the base of 2 cubed is x. The base of 2 to the negative first power is x. So 8 equals x and 1/2 equals x, which is exactly what we see in our graph. But where in between these places are we negative? Because we want to be less than 0. So we can create a table. We know that with logarithms, we have to be greater than 0 with our domain. So I'm going to start with 0, and 0 is not included. Then my next critical value is positive half, and my next critical value is 8, both of which are also excluded. And they're excluded even though we can see them on the graph. They're excluded because we want less than. It doesn't say less than or equal, it just says less than. So a value in between here would be, 1/4 would be in between 0 and half, and 1 would be in between here, and then 9 would be another value outside of that. When I substitute into our piece here, 1/4, plugging and chugging into our calculator, we see we have a positive value. When I substitute 1 using a calculator, we end up with a negative. When I substitute 9, I also end up with a positive. So the only place with which our graph is negative is in between positive half and 8. So our solution set is 1/2 not included because it says less than, it doesn't say less than or equal to positive 8, also excluded because it says that it can't be equal to, just less than 8. And then this would be our solution set. So we did actually get to finish this one. And this should be the last, yes, this is the last example for lesson 6.4.